In this lecture, I'm going to be talking about how to use few-shot learning and using for a name entity recognition, but using span-based approach rather than token-based method. So this article in 2022. Few-shot sequence labeling is a canonical paradigm for tagging models, name entity recognition, and slot filling to generalize on an emerging resource-scarce domain. Recently, the metric-based meta-learning framework has been recognized as a promising approach for FSSL. However, most prior works assign a label to each token based on the token level similarities, which ignores the integrality of name entities or slots. The conditional random fields is an important component for the token level sequence labeling models, but the transition probability between classes in the target cannot be sufficiently learned with very few examples. So that's why this CRF is not useful if you do it directly. So we propose ESD, an enhanced span-based decomposition method for FSSL, and it formulates it as a span-level matching problem between test query and supporting instances. Specifically, it decomposes the span matching problem into a series of span-level procedures, mainly including enhanced. So first we do span representation, then we do class prototype aggregation, and then span conflicts resolution. Enhanced span-based decomposition model that formulates it as a span-level matching problem between test query and support test instances. So this is a two-way, two-shot, few-shot NER task, and the model needs to learn new entities with very few examples. So I have a playlist for few-shot learning, which I have explained all of these things. And metric learning and meta-learning is just one of the approaches, so I just skip that. And in this example, for example, we define a sentence as X and it's labeled as Y, and sub I is just a span. For example, this is a span, and Y sub I is the label of that, and M is the number of spans in X. But we usually filter spans that are very long, for example, five tokens length. We usually do not use them in our enumeration. So this is the architecture that we will go through each of these modules: the first module, second module, third module, fourth module, and the fifth one. So first we do span initialization. Until now, everything is standard because we just use the boundary of this span from left to right. So we concatenate the representation of that, and we are learning this matrix. And then we go for intra-span attention, because rather than just averaging, we are just focusing. It's a simple trick that we have used before. We are using the attention because it's a linear combination rather than just the average, and it's because it's more expressive. Then we use this, we combine with the original span, and then this is much better representation rather than directly using S sub I. And this is feed-forward neural network. This is nonlinearity. Instead of ReLU, we use GELU. And after that, we get the final enhanced representation. The same thing for query. We do it for support and query, the same kind of trick as well. And now we are doing for instance span attention, since different support set spans play different roles for a query span. And for the ICE class that contains k annotated spans with enhanced representation in the support set. Given a query span, so it gets the corresponding prototypical representation. Then we can compute this proto-representation. And like previous lectures, the O type is other is so big, so we divide into separate, usually 3 classes. And now what we are doing is very interesting, that so given a task of support and just a query for the M span, we focus on the M span. In QM, we achieve its enhanced representation. So this is the enhanced representation of that span. Because instead of each word, we are classifying each token, each span, instead of just one token. And now we get, so until now, everything is traditional and classic. But here we are using span refining module in inference. So given a beam state S containing this span, each non-contained span can be represented like this. So we first calculate decay score, and this one is the overlap of 2 spans. So this trick is also used in one of the other papers. And this is a demonstration of the beam soft. For clarity, we set the filter threshold to 0.6. We refine it in order to understand which of those spans have conflict with each other. And these are the data sets: FUNERT, intra. And for one shot, we expect the model to have less accuracy because we're just using one shot. And it is correct because here is just 55, while in 5 shot we have improvement. Or here, 78 we improve if we just use 5 examples per class, then we have much better than we expect, and it fulfills our prediction. So they propose ESD, an enhanced span-based decomposition for few-shot sequence labeling, and to overcome the drawbacks of the previous token-level methods, for it formulated as a span-level matching problem and decomposes it into a series of span-related procedures, mainly including span representation, class prototype aggregation, and span conflicts resolution for a better span matching.